Welcome back, space enthusiasts. During this year, we had two failures in the landing attempts on the moon. Now I want to review the first two successful soft landings in 1966. The Soviet Union's Luna 9 became the first spacecraft to achieve a soft landing on the moon, while the United States Surveyor 1 also successfully landed on the lunar surface later that year. The details of each mission need several hours. In this video, I only focus on lunar lander design, subsystem, and mission profile. First, I start with Luna 9. Luna 9 was an uncrewed space mission of the Soviet Union's lunar program. On 3rd of February 1966, the Luna 9 became the first spacecraft to achieve a soft landing and transmit the first imagery from the surface of a celestial body. The spacecraft consists of two parts, boasting a total mass of around 1,500 kg and standing at a height of 2.7 meters tall. The Luna 9, which achieved a soft landing, took the form of a spherical body measuring 58 centimeters in diameter and weighing 99 kg, positioning on the right side of the spacecraft. Luna 9 was a sealed container pressurized to 1.2 atmospheres, housing the radio system, programming device, batteries, thermal control system, and scientific devices. 4 antennas, which automatically deployed after landing, were fixed to the exterior of the compartment. Additionally, an airbag system designed to cushion the landing was installed outside the station. At an altitude of 75 km, 48 seconds prior to landing, with the velocity of 9,300 km per hour, the radar altimeter, which I'll explain later, initiate commands to eject the side module, inflate the airbags, and commence retro-rocket firing. When the spacecraft was 250 meters above the surface, about half the height of the Empire State Building, the primary retro-rocket was deactivated, and 4 outrigger engines were engaged to decelerate. At about 5 meters above the lunar terrain, a contact sensor contacted the ground, prompting the engines to shut down and the landing capsule to be ejected. It is impacted the surface at 22 km per hour, bouncing several times before settling in Oceanus Procellarum, Ocean of the Storm, on February 3, 1966. After approximately 250 seconds, the 4 petals forming the top shell of the spacecraft open outward, stabilizing it on the lunar surface. By the way, regarding the altimeter, radar and laser altimeter commonly utilized in both aircraft and spacecraft operated by emitting a radio or laser signal toward the surface and calculating the time it takes for the signal to return. This duration, known as the echo time, is then converted into an elevation measurement. If you enjoyed this video, don't forget to hit that like button and subscribe to my YouTube channel. Now it's time to shift our focus to Surveyor. The primary structure of the Surveyor spacecraft was comprised of a tripod constructed from thin-walled aluminum. Extending approximately 1 meter above the apex of the tripod was a central mast. The legs of the tripod contain shock absorbers, crushable honeycomb aluminum block, the deployment locking mechanism, and footpad with crushable bottoms. Each of the 3 footpads extended outward 4.3 meters from the center of the Surveyor. The spacecraft stood at around 3 meters in height. To facilitate launch, the legs were designed to fold and fit with a noise shroud. A sound sensor, canopus tracker, and rate gyros along 3 axes provided crucial altitude knowledge for the Surveyor spacecraft. Additionally, it was equipped with 3 variable vernier rocket engine alongside a solid propellant retro-rocket engine for precise landing control. The retro-rocket, housed within a spherical steel case, was centrally mounted at the bottom of the spacecraft. One of the vernier engines had the capability to swivel for rule control. Although Surveyor 1 didn't carry instrumentation specifically for scientific experiments, it still managed to gather significant scientific data. On landing, Surveyor 1 weighed almost 300 kg, about the weight of a large motorcycle. 63 hours after launch, the challenging part of the Surveyor's journey starts. Less than 2,000 km from the moon, it turns around on a command from the Earth to put it into the proper landing position. Its 3 legs and the big retro-rocket engine and the radar antenna are to be pointed toward the moon as this animation shows. Surveyor speed increases to more than 9,000 km/h as the moon's weak gravity pulls the spacecraft. At this point, Surveyor will have to do its own thinking for landing. The altimeter sends out radar signal to the moon when it senses Surveyor is only 75 kilometers above the surface. It automatically orders the firing of the large retro rocket for 40 seconds and 3 smaller vernier rockets to the proper degree for a vertical landing. A spacecraft slows down from 9,000 to below 400 km/h and burnout retro rocket is ejected as its job is done. The vernier rockets have taken over, continuing to slow the spacecraft down to within 1 kilometer of the moon. The Doppler and altimeter radars were activated. This provided information to the autopilot, which controlled the vernier propulsion system to touchdown. They were checking the distance continuously, not only for distance, but also to correct altitude and correct rate of speed. 3.4 meters away from the moon, vernier rocket cuts off, and the Surveyor falls with a speed of 10 km/h. Falling at that speed sounds a lot, but on Earth, it's about the equivalent of what you hit the ground with when you jump off a desk about 1 meter. Surveyor 1 touched down on the lunar surface on June 2, 1966. The landing site was on a flat area inside a 100-kilometer crater. Some points when comparing SLIM and Odysseus with the Luna and Surveyor. The number and placement of the tanks is a critical consideration in design of a lunar lander. SLIM opts for a single tank, utilize it as the primary structural element of the lander. In contrast, Odysseus features 2 tanks stacked on top of each other, contributing to its towering height, making it the tallest lander in the group. Odysseus and Surveyor have nozzles at the bottom, so they turn it off in the last few meters to prevent brownout or effect on the surface of the landing. But SLIM has a nozzle on the side, so it could use its nozzle until final touchdown, if it was not sheared off. The initial challenge faced by Luna and Surveyor was the uncertainty of landing on a surface whose solidity was unknown. Conversely, SLIM and Odysseus challenged themselves with the task of landing as close as possible to their proposed location. Surveyor 1's landing accuracy was within a radius of less than 19 kilometers. In contrast, SLIM achieved a precise landing accuracy of within 100 meters, showcasing significant advancements in the lunar landing technology. However, they couldn't make a soft landing at the end. While Luna and Surveyor did direct landing, SLIM and Odysseus employed a hovering technique to carefully assess and select the optimal landing spot before touchdown. Avionic instruments such as sun tracker, Doppler system, inertial navigation units, and altimeter remain crucial components of a spacecraft today, especially in mission to celestial bodies like the Moon or Mars, where GPS is unavailable. However, modern spacecraft are equipped with many additional instruments, including advanced image processing capabilities, making them much more accurate than their counterpart from 60 years ago. Final point, after the recording of Odysseus video, it was discovered that the navigation Doppler lidar (NDL) payload couldn't be utilized for landing. Consequently, Odysseus landed without any instrument to gauge distance or correct speed, resulting in a horizontal impact in a rugged terrain area. This impact caused the spacecraft to tilt over. Thanks for watching this episode.